audible on Zoom? Hello. Okay. Yeah. So we can start. Um, yeah. So good afternoon. So I will be presenting my thesis proposal today titled "On Part Whole Hierarchies with an Application to Test and Training." And I'm very grateful to my advisor, Dr. Rawat, for mentoring me over the years and giving me this opportunity to work at CRCV. And I'm also very grateful to my committee members, Dr. Wu, Dr. Etia, Dr. Purush, and Dr. Soon, for agreeing to be on my committee. So I'll start. Um, so there are three partitions to this presentation. One is like the motivation. The second is the papers I published in my PhD and then some conclusions with some future directions. So first, coming on motivation, I would like to start off with a question, and the question is very simple: that do we consider segmentation solved today? So, for example, this is a image taken from Segment Anything website, and this looks like a pretty impressive output. And when we saw this image in 2022 or 2023, we thought that segmentation is almost solved, and that's why we thought that, okay, let's pivot to language. And instead of like just working on pure perception side, we started building models which can do like language-based segmentation. And then eventually we extended this idea to like videos and eventually like 3D scenes of objects, like, and then 4D videos, right? So which is a four-dimensional input. But my premise is that if we go back, there are certain problems about segmentation which are like still not able to be solved. So let me give you like a few examples. So let's say that you want to segment this third tile here. So here, how will you tell a text encoder that you want to segment that third tile? It is very difficult to do that. And now my another question is, what is actually a background in this image? So when we are actually doing panoptic segmentation, we tend to just say that, okay, everything in the sky and in the background, we will collapse everything of that in a single space and we will call that as background, right? But let's say that you are looking at maybe this tree. So when you're looking at this tree, the tree becomes the foreground for you. And then maybe when you're paying attention to it, all the things in the background, like all the other things, maybe this conductor becomes the background. So what I'm trying to say is that it depends on your phobia, like where you are attending to, like what is a background and what is a foreground, and we don't really have a good definition about that. So I would like to take a step back and I would like to take a curious case of segment anything and like how whether it works really or not. So let's say you're given this image of Mona Lisa and you're given a nose, you're given a point prompt on her nose. And let's say you copy this point from 3 times and then you ask segment anything that, hey, can you segment it? So chances are that segment anything will go in and it will output 3 such regions, like 3 such masks. It will output like the nose, the eyes, and then the whole face. So my question is that for the same point prompt, we generally see that SAM is either under segmenting, over segmenting, or sometimes it's doing it quite well. So my question is that for this given point prompt, which one do you think is correct? Is every one of these correct? Is only one of these correct? Or none of these are correct? So as we can see, like it is really difficult to answer this question in the context of segmentation. And it all boils down to the basic definition of what is an object. So my argument is that in computer vision, we don't really know what is an object. It depends on the granularity you are looking at. So like, for example, for me, this whole room is an object, but when I zoom in, this table is an object. And when I zoom in more, the table and its legs are the object. So the definition of the object depends on the granularity at which you are looking. And that is the reason it is very difficult to do it in vision. But in case of NLP, it's pretty easy, because if let's say you're working with language, then you know that you can easily break like a word like dino into individual letters. And these letters are like the atomic unit of language. So whatever sentence you will build from this is going to be a composition of these individual parts to form the whole sentence. So that's my argument, that in NLP, doing doing this sort of like breaking sentence into words is easy. But in case of an image, breaking an image into its constituent objects is difficult because we can't even agree on what an object is. So that's why there was this idea of part-hole hierarchies, that when you're building your neural network, there is a way to organize the internal representations in such a way that, for example, you represent it as a tree-like structure in which, like, at the highest level you have a hole, in which case we have Mona Lisa, and then you have a lower level in which you know that, okay, this nose and this whole thing is part of her face, and then you can decompose it further, like, okay, this is the eye, this is the nose, and this is the right eye. So the hypothesis is that you want to build this sort of hierarchical structure inside the representation of a neural network, and there are two reasons why you will want to do that. First reason is it's interpretable, because you can look at this whole structure and you can see how is your network actually understanding an image. And the second one is that after you build this sort of representation, you can use like this representation for any downstream task. And since it's more interpretable, it should give you better results. So that's so now if we look back at NLP, there is already such kind of structures existing in NLP. So for example, let's say we have a sentence, and generally, like if you look at people like Chomsky and other linguistics, what they have done is they found a way to break this sentence into a part, whole, parse tree like structure. So for example, they can start with a sentence and then they can tell, okay, this is a noun, this is a verb, and this is a noun. So they know how to break this sentence further. So now the key argument is, how do you represent this sort of hierarchical structure in a neural network? And then when Eli invented sequence to sequence, he said, okay, let me do one thing. Let me just take this tree and let me run DFS on it. So I can run DFS on it and I can print this whole sequence, which is just a sequence. If I have this sequence, I can reconstruct my tree. So what he said that, okay, there is no need of hierarchical structure. As long as you have this sequence, you can just train a transformer to go from here to here. So it's possible to build a sequence to sequence model, and which does hierarchical learning. So, but the problem is that if you stick with this kind of sequence to sequence representation, it will not work for vision. And my other premise is that if this type of hierarchy helped us in vision, helped us in NLP, then perhaps it can help us in vision. So, for example, there is a long tradition, like when we took transformer and originally got them working for translation BLU metric, and then we applied it to vision through VIT. So perhaps like this notion of part, whole, parse trees in NLP can be used in vision. So my question is that, like my premise is that we can try to build these kind of structures in our network. And like the reason I chose this topic is because it's like a 45-year long struggle. And if you trace it back, it goes back to David Ma. So you can look at his vision book, chapter 13, which talks about canonical frames. And then when Hinton like started his PhD, until like before they had the AlexNet breakthrough, they had like a sequence of 4 papers which are trying to solve the same problem. And then in the 18 to 21, like 2018 to 21, this is something I call the golden period. And that's what the time when he published this capsules work. And like our lab, like Dr. Rawat and Dr. Shah organized like a workshop in CVPR, which was actually about capsules, where like people like Sarah Sabor and others came to like inform everyone about the breakthroughs. And one good work at that time was like by Dr. Rawat, Kevin, and Dr. Shah, which is called Video Capsule Net. And so that was like a golden period because it looked to me that people were moving in the right direction. They were trying to solve this problem of part holes. And then I think like after 21, it took a turn because in 21, Hinton came with a paper called Blom. And 21 was the era when transformers became really popular, and we had to like swallow this pill of Sutton's bitter lesson, which is that if you take a transformer, give it data and just brute force it, it will learn good enough representations, and you don't need clever sort of engineering inside the architectures to learn representations. And since it could do that quite well and nobody could match its results, that's why like whatever we originally started to do from like 1980s till 21, that did not make sense anymore. And that's the reason like right now a lot of people are going about Sutton's beta lesson. But if you attended this year's CVPR, you would have noticed that there were people like Alexei Efros who are starting to speak up against Sutton's beta lesson again. Like, we believe that it is an amazing opportunity that transformers can do so much, but perhaps there are some better things also which we can do inside the transformer to learn even good representations. So my proposal is that there was this paper by Geoffrey Hinton called GLOM, How to Represent Part-Hole Hierarchies, and that was not working in 2021. So he wrote it as a single author 44-page theoretical proposal. And my thesis is about how to make it work. And I am not saying it fully works. I can never say that because it's like a very big idea and it will take at least a couple of decades to make it work. All I am saying is that we made like some attempts to get it work, and those are like some attempts in my thesis. So there are 4 chapters, and first 2 were published in NeurIPS, the third one was published in ACCV, and the fourth one is under review. So I will try to, in the interest of time, I will try to cover basic intuition, and I will request the listeners to please see the papers for more results and ablations. So this is my first paper called on occlusions in video action detection. And the problem is very simple, that you are given a video and you have these occluders on them. And these occluders are of several types. They can either be dynamic. So you can see that bus rotating. They can be static. In this case, these occluders are static. And they can be realistic, but they are moving. So for example, these bikes and this person walking, they are moving. So the idea is that if you take a video and you subject it to so many occlusions and you tell a network to do segmentation on them or do some sort of task like action detection on them, chances are it will mess up. It's a very simple setup, but the reason we did it is because it actually formed the philosophical basis of how we got GLOM like somewhat working. So I will, rather than focusing on that what were like the benchmark findings, I will try to focus more on the philosophical point, like what other networks can do and they cannot do. So the key observations of our benchmark were that, okay, if you take a video and the occluders are static, their performance drops. And if the occluders are moving, it suffers a lot more. And the best performing model was video capsule net. So now, so here is where our story starts. So let's say that you have this transformer, and so this is like the backbone of transformer, and then you have a capsules and you are having a decoder, and you're training this network to actually go from like the input video and try to like reconstruct it, right? So now the idea behind capsules is that you have a bunch of neurons. Let's say you have 100 neurons and there are 10 objects here. So maybe 10 neurons will bind to this object, 10 neurons will bind to this object, 10 neurons will bind to this object, right? So as long as the number of objects in the scene are less than the number of neurons you started with, you are good. So because you have a finite amount of neural hardware and you partition it into pieces and every hardware is binding to one object. So if your objects are less, it's fine, right? But the problem starts to appear that if you suddenly take a video and you occlude, let's say you put 1,000 objects in it. Now in your capsules, you just have 100 capsules. There is no way 100 capsules can look at 1,000 objects. And that was like the basic problem with capsules, that they were trying to partition a set of neurons such that each set of neurons binds to one object. And because the amount of neural hardware was limited, they could not do more objects. So this was like the problem. So here you can see like this problem actually happening in practice. So for example, if you increase the number of occluders here, technically, like if you have 5 capsule, every capsule should be tracking one object, right? But if you increase the number of objects, suddenly you see like one capsule starts attaching itself to 3 objects. And that's like not acceptable, right? Because we don't want that property. So that's the reason, like, so that's the fundamental reason capsules were not working. And no matter, like, even if you retrain it with more capsules, the fundamental assumption of capsules was not working that well. So this is another problem which I call as object saturation problem. And it's really interesting to see. So let's say that you have an image of height cross width, and let's say this image has 100 objects, okay? So what you will do is you will send in 100 queries and they will do segmentation, right? So now my question is, let's say this image has 1,000 objects. What will you do? You will send it 1,000 queries and they will do segmentation again, right? So the amount of memory you are occupying is directly proportional to number of objects in the scene. But it does not make any sense because the resolution of the image is constant and the decoding memory you are using is directly increasing in proportion to number of objects, right? So that's consuming a lot more memory. Like that's not how the brain might work. So this is a problem I termed as object saturation problem. And my argument was that no matter what transformer you take, it will suffer from this problem where the decoding, the segmentation, the box memory increases in proportion to resolution and in proportion to number of objects. And right now, like if you saw the news, you know that Samsung just overtook Nvidia because memory has grown expensive, right? So for now, compute is cheap, memory is very costly. So we need to save memory. Now here is another way you could go about this. You would say, okay, let me not do detection at all. Let me treat this image as a height cross width image and I will do instance segmentation on it. So for every pixel, I am able to detect what object is present there, right? So in this case, your memory will still be equal to the resolution of the image you're passing, right? So, and that's the assumption behind linear transformer, that if we are looking at a sequence, we cannot do better than linear memory and linear compute. So that is where we all are. So this is the linear attention paper, which came out a year ago or something like that. And that's where our state of the art is. So now my question is, can memory be independent of input resolution? Like it does not matter how big your image is, memory is constant. Like you're able to do segmentation in constant memory, no matter how big the sequence is. So instead of linear, you go O1. And it seems like it's like a very foolish question, right? Because if you see everything, you can't go O1. So now I would like to take a detour and I would like to present this video, which is an implicit neural field. And this was a thing which was done like 2 years ago by everyone in computer graphics community. So the idea here is pretty simple. You take a MLP and you query it with a coordinate and it can give you RGB value. So let's say you have an image of size, height, cross width. You give it a coordinate of height, like one coordinate, 2,2, it will give you the RGB value, okay? So now height cross width, that becomes a batch dimension, right? Because you can query this MLP height into width times and just serially querying it, you get the RGB and you dump it to memory. So the amount of time it takes you is height into width queries in parallel, which you shoot into the MLP, and then you can offload the grid to the memory, right? So that way you take more time to decode because you are doing it in a batch way, but your memory is constant, right? So this is in stark comparison to a transformer where you have a lot of patches, not a lot of time, but you look at everything and it takes a lot of memory, right? So, but here it takes a lot of time, but it does not take a lot of memory. So people were already doing this for computer graphics, and this is an implicit representation, and this was its biggest selling point, that it could do machine perception in constant memory. And just imagine that you have 2 hour video and you can compress all of it in an MLP and do your perception. Since you don't have to pay for 80 gig or 20 gig, like 250 gig GPU anymore. So now the problem is that they had this model, but it was purely stuck in computer vision community, in 3D community, and they were doing it for 3D scenes. So they had to rely on this ray tracing idea, which is that you model the world in a 3D scene and you shoot rays into it, you take points along it, and for each point you're trying to predict like how much opaque and good it is, right? So they had this interesting idea, but it was not working for 2D perception. And they were not able to, and they were stuck with this thing in 3D community, but they had actually invented this. Now, people in the 3D community, they were saying, okay, they were not concerned with this memory property at all. Like for them, it is just a way to do perception, but they are like not interested in that property. What they were interested in is that you give us an image of 3D scene and we want to construct a point cloud. And it does not matter how we get there, as long as we can get a very good result. So the argument is you can replace MLP with a transformer like VGGT, and you can get a really good segmentation or point map from the scene. But the argument here, the counter argument here is because you replaced it with a transformer, you lost this constant memory capacity. So if you're looking to do machine perception, let's say you want to do 10,000 images in around 48 GB GPU, chances are that because you're doing parallel perception, it won't fit in the memory. So this is the trade-off, and this is the exact trade-off which we are trying to exploit. So that's why I will ask this question again, which might not seem that weird now, that can memory be independent of input resolution, perhaps a constant? So that brings us to this idea of Hinton's Bloom architecture. And it's a really interesting way to look at the internal representations of a network. And what you can actually see, so generally we don't care about what's happening inside the network as long as the last layer is doing the job. But here what he's doing is that, let's say your transformer has 5 layers, 1, 2, 3, 4, 5. So these are different levels of the transformer. And in each of the levels, there are L tokens which you are injecting. So in your image, you flatten the tokens. So height into width tokens are the sequence length. Now, the main point is that at every location, there is a d-dimensional vector. And at the lowest level, all these vectors are pointing in a direction. So there is no structure to them. They are just pixels. But as you move up, these vectors start agreeing with each other. So for example, vectors which are part of the node will start to be pointing in the same direction. And then as you move up, the whole face will start pointing in the same direction. And then as you move up, it's the whole scene. So the idea is that as you are going inside the transformer, you can start from pixels and naturally a grouping emerges. And that grouping is actually encoded in the phase of the intermediate representation. And here is another analogy. You can assume that this is a rectangle and the volume of this area of this rectangle is constant. So this is something I call the compute law. So if you have a very long sequence length, you cannot afford to have many layers on a GPU. But if you have a large number of layers, you cannot afford to have a very long sequence length. And so the area of this has to be constant for your memory law, and there is no way to get out of it, right? But it seems there is. And the way you get out of it is by using his Bloom idea. So he came up with this beautiful idea and there was no proof. He just said it should be there in a transformer. It was pure theory. So we showed it practically. So what this is basically a transformer, but this is not an image transformer. This is a video transformer. And the image is repeated across time. So let's say you have an image. Your transformer can only look at 8-frame video. You take the image and repeat it 8 times. You pump it through the transformer and you're looking at the internal layer of the transformer and performing TSNE clustering on it. So we saw like these beautiful islands emerging. And before us, there was only one paper which did it. It was called the Dino VIT feature descriptor paper by Yossi Gandelsman. And then around after we published, like Dino V2 came up, but they were only doing single object. They were not doing it for multiple object. So if you see a lot of OCL papers, what they will do is they will take an image and their object will be just in isolation. And because they can't do this kind of detailed segmentation, they will never show it. Only like if you go to the recent Dino 3 paper, you will see that they're somewhat starting to do it. But we already showed this back in 23. So that was like the basic understanding that, okay, Hinton's philosophy was correct. Hinton's philosophy was correct. And if he's saying something, it is working. So maybe all other things he's saying might also work. So that was like the premise which we were talking about. So the limitation of our work was that it was all philosophy and it was hijacked, like because no one in the community was trying to believe it. So we had to work and get the actual empirical results. So this is my second work with Dr. Rabat, and this is also in NeurIPS. and this is called asynchronous perception machine. And here the task I'm tackling is test time training. So there is a reason I'm choosing test time training, because it's one of the hardest tasks you can do. You have to adapt to a single test sample without any training, like without any pre-training. So let me explain the task first. So generally you take a network which is like this Y shape, and what it has is a backbone, a SSL head and a task head. So what you do is that you first do undergo a training phase in which you take an image and then you mask a part of it and then you reconstruct it. So you can see this branch is a traditional masked autoencoder branch. And in addition, you are trying to predict the segmentation mask. Okay. So you take a bunch of data set and you wire up the whole thing and you train it with backpropagation. That is really good. So this is the training phase, and the test time training kicks during the testing phase. So what you're given is, let's say, an image of a dog, but it's not a real dog. It's like a dog, but it's massively corrupted. So in real world, let's say you are going in snow and you capture an image and it's massively corrupted and you want to adapt to this. So how do you do it? You are not given any label. So what you do is you pump your image through this backbone, you mask parts of it, and then you go to the SSL head and you try to reconstruct it, and you update this whole thing in a loop. And because this whole branch, the upper branch never uses any label because you're just trying to reconstruct it, you can afford to update the backbones for a few iterations. So after you're done, after you have a new set of weights for your backbone, you pump your image through the task head and you get the segmentation out. So the idea is, by doing these couple of iterations of gradient descent using a SSL head, you get better results than just doing a pure feed forward using segmentation. So that's the argument of test time training. So the problem in this case is that if you look here, this backbone is shared between SSL head and task head. And if you're doing backpropagation and this top head, this backbone is generally going to be a VLM, which is like 24 layers of attention on it. So because this backbone is very big, and because you're training it during, because you're doing a couple of test and training iterations on for every test sample, it's gonna take a massive time. So like for example, for one test sample, it is gonna take you like 4 or 5 seconds to adapt it. So if this is a very big model, how do you adapt it? And the answer is, how do you efficiently adapt this? So our answer is that don't adapt it at all, rather keep it frozen. And the idea is that you keep the backbone frozen, but instead you set a classical distillation loop in such a way that the backbone is frozen, but you have a small student. And what this student is doing is that it's mimicking the features of the backbone, and this loss is a standard MSE loss. It's not a cosine loss. It's a very interesting conversation, but I'm not talking here right now. It's a MSE loss. And the idea is that the student will start predicting better features than the teacher. And then you can just replace this whole backbone with the student and do adaptation. Okay. So now the next question is, this is just distillation, right? You take a student, you take a teacher, you distill the representation like it's normal distillation. There is nothing special about it. So what's special about it is that the structure of the student is not your typical CNN or a transformer. It's just a 5-layer MLP. And it has a curious property that even if you initialize this MLP with random weights and you train it, it's able to converge. With just one sample, without any pre-training, it can learn good representations. And it gives you better features than the teacher. So now this property in which you take any architecture, random weights, just one sample and have it overfit, you cannot find it in any other architecture we tested. We tested it with ResNet transformer, VIT, even we tested it with a normal MLP, it does not work. So this property where a MLP can overfit on just one test sample, that's a rare property. And it's based on 3 ideas, and I will explain those ideas. So this is a reinterpretation of a feature grid. So for example, let's say you're given any model, you take an image, you go from an image to a feature grid. Now our idea is, so generally this model is like a parallel model, like a VIT or a transformer. What we changed is that there is a new way to look at this grid. So instead of looking at it as a cuboid, you can actually start looking at it as at this location, which is 1, 1, there is a d-dimensional vector here. And you can imagine that there is a student to which you give the whole image and the location 1, 1, and it gives you this red vector in parallel. Okay. So now here is the big thing. So here is 4 by, so this is 4 by 4. So this is 16, these are 16 locations, right? So if you're given 16 GPUs, you can spread out this APM at 16 GPUs in parallel, and you can feed one query for every location in parallel to it. So what will happen is that your inference will be super fast because suddenly you found a way to parallelize all the queries across batch, right? But if you had 16 tokens and you were doing attention, then you will have to wait for every token to interact with everyone, and then you will get the output, right? So that's the reason like my attention is slow. And this is a sort of asynchronous processing, which is really fast. And it has the ability to just predict whatever features like this big model, like transformer is predicting, and it works really nicely. So this is like a plot where I'm trying to show that if you take a VIT and you have this student network, which you distill from it, and you're comparing their inference times, what you end up with is something which is 1,000 times faster than a transformer, and it gives you better results on image recognition than the best open clip model out there. So this was the main thing, that you could make something which is asynchronous, spreads across GPUs, and it's very fast as compared to attention. So this third is a fundamental geometric operator for learning machines, which I call the folding unfolding mechanism. And it doesn't have to be this paper. Like this mechanism is going to hold for any learning machine out there. And this folding unfolding mechanism is as follows. So let's say you have Mona Lisa and you have these 4 tokens in it, and each of the tokens, each of these patches is positionally encoded. So now if you were to feed this Mona Lisa to a normal MLP and ask it to reconstruct the Mona Lisa back, it won't work. Because as soon as if you have 2 dense layers, information goes in and then gets mixed, and there is no sense of positional information. That's why a normal MLP, even if you train it on CIFAR, you get 50% classification, no ability of reconstruction. So here is how you feed data to a MLP. You change the way you are feeding it. So now if you have 4 patches of the image which you are trying to decode, and what you do is you flatten your whole image like this and you attach a positional encoding to it. And now suddenly it has this whole context in it and it can start predicting the face. Okay. So now you can copy these queries across locations and you will be able to do RGB reconstruction. Now, why this was a big deal for us is because when originally Frank Rosenblatt invented perceptron, it was thought MLPs cannot do segmentation. And that's why we invented CNN in transformers. But we had the first proof that MLPs can now do segmentation as well as image reconstruction, which means that we are no longer bound by that. And that's actually closer to universal approximation theorem's understanding, right? That a dense layer should just do everything. So now what I want to focus on is just one column of this, which has an image and a positional encoding. And this whole column, so this is a general data structure. You can imagine that it's like a tape. So you feed symbols to a machine and it can decode. So this is something I call the trigger column. So how it works is you take an image, one CNN filter, you attach, like you flatten the output, and then you attach the positional encoding. So this is the unfolding phase. And then when you are trying to decode, because this I is shared across locations, you can just attach these hard-coded integers 1, 2, 3, 4. This is the unfolding phase. So now your learning machine is basically oscillating between these 2 states. One is a folded state, one is an unfolded state. So these are the learning iterations you are doing. So this is folding, this is unfolding. So you do this like a couple of times and then an MLP goes on top and it predicts. So this is the unfolding phase and this is the folding phase. So unfolding, and you do this like for a couple of iterations. So for every image, you take the MLP and you do this, you undergo these cycles of folding, unfolding, and you basically you feed it the image, you try to reconstruct it and do it in this loop. And the learning is just this oscillation between folded, unfolded state. And then the architecture begins to show like amazing properties. So there is like this first property, which I call the interpolation property. So if you are given any two images, what you can do is you can compute this intermediate vector like v1, v2, and you can do linear interpolation, right? So this is what you get. You are able to interpolate between any two images of the world. Okay. And now here is another thing. Let's say this space is of 100 dimensions. So because you have a 100-dimensional space, the linear hypothesis states that all the images in it will be in a subspace, right? So what you can do is you can pump, like say, n images to it, get n vectors, form a subspace, and just do interpolation in that space. And what you end up with is a fantastic generative model. So we never showed the generative model in our paper, but I did do those experiments. So now here is the fact that we never set out to do this, and it happened on its own. The only math it involved is this folding unfolding operator. And that's also just a positional encoding attached to it. So now the only argument I will give is that generally in class we are taught overfitting is bad. In NERF, because their MLP was overfitting everywhere, they just overfit as much as they can because they are able to interpolate from new viewpoints. So the more you overfit on scene, the better it is. Now, my argument is if you are given a lot of 2D images, all the 2D images of the world, and you overfit on it, basically what you gain is generalization, right? And that is, if you overfit on that, that's actually a field in which you can interpolate. So that is what APM is trying to do. So this is a proof that you don't need parallel perception like what Dino is doing. So in Dino, okay, you take the image, you do parallel perception, and then Dino gives you this output, and you do it the way I am saying. You query it one by one in a constant memory. And what this is meant to show is that you end up with the same feature grid. And the way you test for this is you take the feature grid, take the difference, and the white region actually shows you where the error is happening. Okay. So you can see, okay, most of it's black, and there is some white, which means it's good. Okay, so it's doing a good job. There is one other thing it can do. So what it can do is, generally in a transformer, what happens is you take your tokens, you pump it through the transformer, then you have a CLS token which cross attends to all the patch tokens, and you drop the patch tokens and you just classify with the CLS token, right? So what you're doing is you're losing all the spatial information, and everything is held in that one token, right? The CLS token which you are using for classification. So what we actually showed is you can go the opposite way. So if you give me a CLS token from a transformer, I can actually predict all the patch tokens which it attended to. So this is an inverse model of a transformer. Okay. So this is what I'm trying to show here, that if you have an image and you do multiple iterations on it, the loss drops, and you can see this cat is actually getting broken down into its body parts. So this is my full diagram, and this is like some results we obtained. So we obtained some better results than the best model of OpenClip at that time. And it held across multiple ImageNet samples and multiple settings. So now the problem in our method was that it only worked for images, and it was only doing classification. So it was not doing dense segmentation. And the argument is, if you go to this figure, you can't really test the quality of this grid if you can't do a dense task using it, right? So that's why in our third paper, what we do is we propose this new network called a frame forgetting network, and it is basically doing test and training on long videos, which are like hours long, with certain changes. So the key selling point is that it is fast, it is accurate, and it works for dense tasks. It can work for semantic instance panoptic video segmentation, and it can work for depth estimation, which takes care of the argument that you could only do recognition using the APM model. And now here is the technical problem. So generally a video is a sequence of frames which your model encounters, and that's a running stream. It's a streaming scenario. You don't have access to the future frames, right? So now what you have is, let's say, generally all sort of recurrent models you build, they will lie within a window. So let's say this window size is 3. So this window only contains F2, F3, F4, and then the next time the model is processing, it will shift the window by one step, and it will process F3, F4, F5, okay? So now this is a sort of overlapping window, and the problem in existing models is that in this window, they were looking at F2, F3, F4. So they were doing a gradient update using all these 3 frames. And then when they reset their window, they have F3, F4, F5, they were doing a gradient update using these 3 frames again. So basically, if your video is of n frames and you have k frames in the window, the compute you're incurring is n into k, with a lot of duplicate compute between overlapping windows. Okay, so we saw that this is like not the way we should be doing it, and this is the reason when you were doing test and training for a 2-hour long video, it took us 8 hours, and that's the reason you could not deploy it in real world. So what we do is we got this time down from OK to O1. So it does not matter how long your window is. You will only incur the compute cost, which is a constant per window. And how do you do that? And it turns out there is a well-known idea in algorithms called Kadane's algorithm, which says that if you have a stream of bits, you can have a window, and all you have to do is you maintain the running sum of that window, and you subtract the frame which went out and the frame which came in, and suddenly you have a new sum of your window. And this only requires you to subtract 20 and add 60, which is 2 operations per window, right? And no matter how big your window is, so if your window is K size, you will first incur the cost of making that big window. But once that window is there, when you start sliding it, it's just 2 operations. So our idea is that, okay, if this algorithm exists in serial memories like arrays, it should exist in a parallel memory like a neural net. And that is what we basically exploited. So the idea is, let's say you have these 8 frames, you have these 8 time steps, and let's say you are doing test and training on every time step. So because you're doing test and training on every time step, your backbone is evolving over time. The weights are changing. Now let's say that you are at this window and now you move it by 1 step. So now F1 is the frame you want to forget, and F6 is the new frame which is incoming. So what you basically want your network to do at this point. So at this point, you only have access to F6, which is the current weights of the model. But what you wanted to learn, you wanted to learn that, hey, before I adapted at this T1, whatever features were there, you should recover that feature, right? Like before adaptation, if you had some feature F1 at this point, when it's time to forget it, you should predict the same feature. And what you can do is you can basically parameterize your model in this way, and you can minimize the L1 loss and your L2 loss, and then just one gradient step, and it works really well. So now here is another problem, which is I call a anticipation mechanism, and like it was like Dr. Rawat's idea. So here is the problem. So let's say that you are moving, you have a camera, like you have a video on a CCTV camera, and it's nighttime. So there is nothing changing. Okay. Everyone has at their home, the scene is static. You have a model sitting there, and if the scene is not changing, it should never adapt. Right? If the scene is changing rapidly, it should adapt. So the idea is, how do you figure out for the incoming frame whether it's time to adapt or not? And the idea is you just compare the current frame with the next frame, take the pixel difference, and you're good to go. If it satisfies like some threshold, it's time to adapt. Okay, if it's greater than some threshold, it's time to adapt. And otherwise, it's time not to adapt. You just copy the backbone weight from 5th time step to the 6th time step. So, when we were designing this function, there are 2 problems in this. So let's say you have a cell phone, okay, and you're capturing a video, and you slightly rotate your cell phone. Okay, so now the scene is same, but because you rotated your cell phone, it's going to be same pixels, slightly rotated. And if you do L2 loss between that, it will not work, because it will say there is a lot of L2 loss, right? Because pixels change, the representation did not change because it's the same scene. So that's why what we did is we actually chained together the pixel-wise difference along with the latent difference, which is like if you have a network and you look at the deeper layers, you take the L2 norm between the features, those don't change to minor rotations in the input space. So that is the invariance property which augmentation enforces. So you need a base model which is trained for augmentation, invariance. Okay. If you take an equivariant model, it won't work. And then you change it, and then you calculate like this surprise. And if your surprise is bigger than, like, you have this moving window of surprise. So whenever you encountered a frame and whenever you adapted on it, you have a lot of surprises. You compute it, and there is a buffer. and you just look at the mean of the surprises and the variance of surprises in that window. And if you can do that, then you can actually compute like your threshold dynamically, which is just one variance away from the mean. And the reason we took like one standard deviation is because of the central limit theorem, which says that most of the probability mass is within one variance. We tested it with different variances, but we found one variance to be optimal. Yeah, so this got down the compute time from OK to O1, and it turned out that you could build some sort of algorithm like Cardano's in a distributed memory, and we got like really okay results. So like this was the best method, TTT MA. It used to take 4.1 seconds per frame, so we got it down to 0.7 with, I think, we improved from 37 to 45. So basically it is like you are getting better results with lower compute cost. And now here is another point. So let's say that you are sitting on a model, and every time you're doing test time training, you are trying, if you do test time training on every frame, then your model will actually forget all the knowledge it learned in the past, right? It will overfit to the current video and it will lose a sense of its representation. So let's say you take a model and you adapt it for every frame, okay? And it's a normal model like a mass to former. So what you see here is that it degrades over time. So this is hours. So over a 3-hour video, it degrades. But in our case, because you're also forgetting it, like as you're moving the window, you're forgetting the old one, the performance remains constant. So like it stabilizes across the time, which proves that it works for 3-hour long video. We didn't check it for like a day long video, but I think it should work, but I will have to check it. So that's the main point. So the key takeaway is that we think forgetting is bad. That if our model is catastrophically forgetting something, it's bad. But if you think it from a principle of locality, which is that if you are only operating on frames inside the library, you don't really need to know anything about outside the library. So if you can just maintain a small buffer and just retain that context, then it works really well. You don't need to remember everything. So you can use forgetting to your advantage in this scenario. So now I want to I want to just say that we got the compute time down from ON to O1, right, per window, but it's still slow. And why is it slow? The issue is backpropagation. So let's say you have 3 layers. The first layer will only update itself when it receives the gradients from all the layers behind it. So if your network is 1,000 layers deep, it will have to wait for 1,000 time steps for the gradient to flow back, right? And because there is so much waiting, it means that your model is just sitting idle on your GPU and it's not doing anything. So just for optimization, we are using gradient descent. Sorry, we are using backpropagation. Because of its waiting, we are not able to do even better. So just imagine that this time is 0.7 seconds with backpropagation. If you got rid of backpropagation and replace it with some sort of forward learning, you could slice off this time a bit more. Okay, which makes like TTT for real world deployment really feasible. So now this is my 4th paper, which I call as layery query network, and it's meant to actually, so I just have 2 slides because it's still under submission, and I want you to just take one idea away from it. So now let's think about what our standard assumption is how a neural network works. So let's say you want to predict what's at layer L. What you will do is you will have to pass through all the layer L to get the answer at layer L, right? So now this is what we say. The scaling law says that if you have to predict something at deeper layer, you need at least the amount of compute about what depth it is. It's a linear compute, right? So what I'm saying is you can get it down to a constant, O1. And the way you do it is as follows. So you take a student, so you have these all internal representations. You can actually look at each representation and you can assign a coordinate to it. So let's say this particular dude, sorry. So this particular guy is at 2nd layer and maybe 3rd and 4th pixel, right? So let's say you train a student, what it does is it takes in the image and you tell it, okay, hey, here is 2, 3, 4 index, just give me the representation and this value, okay? And now you train it. You train it in such a way, you train a coordinate condition network in such a way, and you do it for a bunch of data set, okay? And then during inference, you just swap this big guy with the small guy. And during inference, you directly query it with the last layer index. and it will directly output you the last layer index. Okay. Now there is one good thing about this. So let's say your student was equal in architecture to the teacher. Okay. So let's say you want to distill all these layers. What you will have to do is your architecture will have to be similar to student teacher's architecture, and that will not be good because it will still take a lot of time for distillation. Alternatively, you can have a small student and you can only distill the last layer. But that's not gonna work because we are not concerned with direct mapping from input to the final layer. We want to actually know the whole trajectory of how the input evolves over the latent space. So it turns out this is a way to do distillation which combines the best of both. Why? Because you can inject the information of all the queries, and the size of the HQN has nothing to do with the size of the network you are distilling from. Okay, so that is the core argument here. And here is what happens. So let's say your teacher was a big model of 24 layers, but you only distilled 20 layers. Okay, now technically, since it's coordinate condition, you can query it with 24th layer, right? During inference, you can control that, and its performance will actually improve over the teacher. So if you query it with 30 layers, it will actually outperform this 24-layer model. Okay, so what I'm trying to say is that the depth of the neural network is also a spatial dimension, and the deep learning law, the scaling law, does not hold. It does not have to hold. So now the only argument which is killing my premise is that I am using a teacher network to distill the knowledge, right? So I'm not achieving true O1 training. I'm achieving O1 inference, but I'm not achieving O1 training because this whole thing relies on distillation, and it's making the assumption that teacher is strong enough to give the correct outputs to the student to learn from. So but the use case right now is you train a big teacher on a big GPU, like in cluster, and then when it's time to make a student, you just learn a small student in this way and roll it out to a edge device. The notion of training a very large model from scratch on a small device is something we still haven't figured out. So that's my thing. And now I will just end with like a couple of future directions, which I think like are interesting enough. So as I mentioned, we were facing a lot of problem with backpropagation, and we did try doing forward. But there is one other problem in forward is that it cannot match backprop. And here is another problem. So let's say you are given a weight. So this is a basic gradient descent equation. And if you see here, when you're doing weight update, you have to do two things. You have to compute the weights and you have to compute the gradients. So the amount of memory you are occupying is twice. It's a copy of the weights and a copy of the gradients, right? So if your brain was working this way, it means that for every synapse, it's storing gradient somewhere. But that seems inefficient. Because to do this optimization, you're using twice the memory, right? So now gradient forward is still doing this for every layer. It got rid of computing gradients at every layer and storing them, but it's still doing this for each layer. So that is something we need to solve. And then, yeah. And then there is one other thing I call as sleeping phase. So it is as follows. So let's say that you are sleeping in the night. So all your senses are closed, right? There is no input from the environment, but you're still thinking. So there is something happening in your brain, which has nothing to do with perception, right? It is something happening inside your head, some sort of gamma wave, and that's like a sleeping phase, right? So that's not perception. It's not seeing anything during the day. But in the night, something is happening in the head. And my insight is that if you build this kind of sleeping mechanism inside the network, it will do really well. And now the thing I want to end my proposal on is that I have been working this ground direction for 5 years. And now what I'm led to believe is that transformers are not a good model to implement GLOM. And I will give you the reason for that. So this is a slide from Rob Fergus when LXNet came out, and it was a paper called Visualizing and Understanding ConNets. And what he showed is that at the lowest layer, we have these filters like these circles, and the highest layer, we have these people, right? So the grouping is going from lowest layer to highest layer. At highest layer, there are objects. Now look at Hinton's diagram. At the lowest level, there are pixels. At the highest level, there are objects, right? Now look at the clustering inside a transformer. So at the lowest level, you can see a broad level clustering, and at the finest level, you see the parts emerging, right? So now you can see that it has inverted the hierarchy because it should have been these parts first and then the grouping later. But the grouping in transformer is happening in the lower layer, and then in the last layer, it's giving you a part. So it has essentially flipped this whole hierarchy. And it turns out that this is how attention mechanism works, and this is how the clustering looks like. So that's why, like, I think it does not feel intuitive, and there has to be like a better way to implement part whole hierarchies. Yeah. So that's all I had, and thank you so much. If there are any questions, yeah.
All right, great. So any questions from the audience? If not, I think maybe you can hand the question. Yes, question.
Hello.
Your mic is open.
My mic should have been.
So Dr. Atia, Dr. Sun, thank you for joining. Can you hear me?
Hello, yes, we can hear you.
All right, great. Hi, Dr. Atia. So who's this thing? All right, so you have any questions for Rajat? Rajat can come.
Yeah.
Uh, I have a couple of questions. Thank you, Rajat, for the presentation and the work.
Thank you.
And good work with all these NeurIPS papers, acceptances, and such. So I have clarification questions because
Sure.
I probably didn't read the papers very deeply. So for example, when you mentioned this that the memory stays constant regardless of the image size,
Yes.
by doing these queries, I guess you're doing them per pixel, right? So,
Yes.
but don't you still have to ask one query per pixel if you want to process the entire image, which means
Right.
that the time itself is going to increase.
That's
Uh,
true. So
like,
now, so here is the argument that if you look at a scale of perception in a standard attention, the time is constant, but the memory is very big because you're keeping all the patches in memory. But there is an alternate scale in which you are taking a lot of time, but you are not using that much memory.
okay,
So
I
what we basically did is we just said that there is a extreme direction to this other scale, and
okay,
choose what kind of machines we want to build on these scales, and that depends on the device we are concerned with.
yeah. And is the work that you did there mostly focused on the last on one layer, right?
Yeah, but the last paper I presented the layer query network that actually got it working for all the intermediate layers also.
Okay, I see. And are the types of problems that you're able to answer, for example, better related to the whole image? For example, you're asking questions such as what's in the image, what are the objects in the image, versus, for example, drawing outlines or segmenting every object, right? Did I get this correctly?
Yes. So there are three ways to do perception. One is a language-driven perception, and then the second is what you said, a scribble. But there is a third way in which what happens is that if you are doing just a classification kind of recognition, the perception, like the segmentation, emerges naturally without any labels. And that is like you give it just a classification and it just predicts like this whole structure inside itself. Like it organizes its internal representations in that way. So that is what like I was trying to do. Now, I agree with you. The problem is that if you are given an image, there is no annotation to what the part whole hierarchy should look like.
Yes.
And even if a network manages to encode it, we have no way to evaluate it. So that is the main reason why like part whole hierarchy kind of stuff, it's very difficult to evaluate it. But like right now, what we are doing is that there are these data sets called part ImageNet, which have these hierarchies built in, like people annotated it. So a next step would be to take these data sets and try to get our network working on them.
Okay. Maybe one more general question that you can answer. So what's the, I mean, you have many chapters. What is the coherence point between these
The
different chapters? Is
the
it just
coherence point is that the internal representational field of a neural network is it is a field and you can query into it using positional embeddings. So like inside the network, like you have
Mhm,
this structure which it builds in the representation, and you can jump to any representation by mapping that manifold of representation onto a coordinate space and
mhm.
querying it accordingly. So now if you have a representation and you want to like query it, you have to assign coordinates to it. But the way to assign coordinate to it is through a positional encoding. So at fundamental level, it's like a memory, and in a memory, you need to be able to query and write. So that is what it is sort of achieving.
Okay. Thank you, Rajat.
Thank you.
All right, thank you, Dr. Atia. So, Dr. Sun, you have any questions?
Hey, thanks for the presentation. That is a great work. You're just, I think like later we might have some collaboration together in the occlusion study. Like right now I do some experimental mechanics. Sometimes we have like wires blocking their interesting structure features all the time. Right now we are doing image level like de-occlusion or deep tech study. That is one that Rajat's like chapter one work could be used for in my study. And second part, I do remember you talk about nerve, right? Right
Yes.
now we are trying to use a camera video and together with indoor drones to create like a relatively small size like data sets. Think about like if I have 10 cameras rolling all the time doing the experimental mechanics dynamics experiment, the size of images is very big, like several terabytes. So we are thinking about like shifting to a smaller size nerve to do a 3D representation in a dynamic way. Maybe I already forwarded your like proposal to two of my students. Maybe they will reach out to you guys soon.
Sure. Thank you
Yeah,
so
yeah,
much.
yeah. I only have comments. I'm learning. Thank you so much.
All right, great, thank you. So, Rajat, we can step out and then.
Yeah.